Hello everyone to the lecture in ICT for Smart Grids called Data Analysis 1. We deal with the background today. My name is Vincent Lutzko. I'm a PhD student with chair. And if you have any questions in lack of direct visual confirmation that you understand everything, just send me an email if you have any issues with the context and the content of today's lecture. This will be the intro course. We will cover mostly mathematics, mostly foundational things. And we will also explore the data set. So everything that I'm telling you today in terms of describing data sets or things like this, we will apply it. We have, however, at the chair dedicated courses for statistics, so I can only cover a very brief excerpt of what is covered there. And I'm very sorry to tell you all, you will not be a data scientist after these 3 courses, and you will also not be a machine learning engineer. And we're really only scratching the surface here. So please be aware that this is for context in the ICT course, but it's not meant to be the be all end all solution. So in the next session, just for guiding you, in the next session we will introduce the machine learning, where I'm going to give you some sort of a short introduction into what machine learning traditionally can do, how it works in rough sketches. We are going to do a linear regression example, and we're also going to look at neural networks. And in the final session, we will look at the deep learning, because everybody's doing deep learning this time so on, and we will have a hands-on for that too. So this is it's an exciting 2 sessions that we have in front of us. And I want to dive right in. So in the last sessions, you heard about databases and how to store all the data that you gather in smart grids in the future. And the database is really the foundation for the data set. So a data set in terms of data science is typically a collection of data points. so each data point, you see this here in the lines of this matrix D, so the rows. So each data point consists of single parts, and these single parts are called features. A feature can be anything from a single number or a collection of numbers, or it can also be other kinds. We'll look at that in briefly, but it's important to understand that this data set really is a high dimensional association of single points. So in the context of smart grids, this could be a time series, where for every sample I, so the samples I would refer to time steps, and the features could be anything from the voltage at that time to the power drawn at that time to anything derived from these quantities, which are physical quantities. You could also imagine all sorts of elements that you have stored in your database. You can read them as a feature and use them as a feature. This is strongly problem dependent, but you're getting the hang of it, what this already means. So a feature is a hard thing, and in computer vision, these features that are part of images are typically pixels or derived quantities, and then but they can be pretty much everything. But they can be fit into 3 major categories, let's say. One of which would be numerical, and pixels would have a numerical value, typically encoded in red, green, and blue. But in general can be any kind of numerical element. So it's be it integers or real numbers, anything like this. There could also be categorical features, something like well, the category of a class, for example, or ordinals, which just means ordering. These categorical features are typically hard to work with. So if we have something like a label, where we say, okay, it could be red, it could be green, it could be microwave, it could also be something like power. This feature is hard to work with because you have to map it somehow. A machine or an algorithm doesn't really want to deal with strings, for example. And label encodings, so to speak, are very convenient for engineers or for data scientists or any kind of user, human user that interacts with such a system because it makes it so much more interpretable. However, what is more useful for the machine is actually this one-hot encoding, where basically you map from the label encoding that is understandable to something that's just more efficient. Because if you look at the example that I gave you here, you have the red-green microwave, and the one hot encoding would be for the first sample, for the green part, you would have the one at the part of the location which codes for green, and the zero which codes for the location of red, and the zero which at the location which codes for microwave. And for red, you would have the 010 because the 1 refers to the status of red. And in the microwave setting, you would have the one at the very last element. So this is basically a mapping. So the two can be mapped from one to another. This is this is possible, and in most cases, it's even needed because otherwise you're kind of at a loss, and you realize, okay, now I get a good prediction or get some result, but I don't remember which, or I cannot interpret which label this actually belongs to. So a one-hot encoding should always be mapping back to a label in the end. This is, as I told you, it's just for typically it's used for processing it in a much more easy way because you don't have to deal with strings anymore. Okay, from features to something more statistically. If we have such a data set and you have some column in that data set, so not a row anymore, but a column referring to some major overarching feature, something like, say, power, and now you want to look at the power over all the data samples, then you're suddenly confronted with a problem of how does this actually look like? So you typically, if you have a data set, maybe a new one, a new part of the data set comes in, or maybe you have to inspect some part of a data set, you always want to explore how the data looks like. And so one option is, of course, to just plot it. So do a scatter plot or something like this and just look at it visually. But this can sometimes be very, very hard, especially if you have higher dimensional features or if you have combined features or if you don't have a screen available or something like this. So in the end, what you're typically going for is looking at statistical values that tell you something about the data set or this slice of the data set. And we're going very quickly through the most common ones. You should have heard this already in the course of your studies, but we're going through it again just to make sure you have a grasp of the main concepts and you have a really good understanding. So these quantities or qualities of a distribution are scalar values. So we're really trying to reduce all of the data set to something much more graspable. So now it depends on how far we collapse the whole data set. Because typically, I mean, the data set is big, we can't really understand it, and therefore we're trying to summarize it, if you will. And the easiest summary is taking the mean. This is basically the average value of the data. And it's associated with just with a sum of all the values, and you divide by the number of values, and then you get the classical mean, right? This is a single number that tells you already something about the data. Okay. Another option would be the median, which is again a single number that tells you something about the data. And this is just the middle value of the data. So to have a middle value, you should order the list first. So the data should be ordered for this. And then you get an understanding for the data because the middle value tends to be the one that splits the data exactly in half. They are very close to one another, depending on what kind of distribution you look at. So for example, for something like the normal distribution, which is the most common one, they're exactly the same. Just really plain simple, same value. However, if you have outliers, so something that goes, so you have a single value that maybe was a sensor error, or something else happened here, which is corruption maybe in the database. And of course you have suddenly an outlier. So out of 1 in the measurement from 0 to 5, suddenly some bit flipped and you have a 20. This makes a huge difference for the mean. It doesn't typically make a huge difference to the median, because the median, things just get shifted possibly by 1 step, and that's it, and nothing else. So the median is just really the middle number. The mode is the most common number then. It's not terribly useful in most cases, so I've never used it, to be honest. But it's still a worthy inclusion, because it tells you something about if things are all right, for example. So this is also a worthy inclusion. Something else that people look at are the quartiles. There's really 3 of them. The first quartile, the second quartile, and the third quartile. And the first quartile, that it cuts off the lowest quarter. So you take the lower half of the data, so just the lower half, the left of the median, so to speak, and you take the median of that one. Then you cut off the lowest 25% of the data. Second quartile is exactly the median. It cuts the data in 2 pieces, which are of equal size. And the third quartile is just the median of the upper half. So it's exactly the mirrored version of the first quartile, so to speak. And depending on the distribution of data that you have, this tends to be very informative too. Now things get dicey. We have the variance. And the variance looks at how much your data differs from the mean value that you calculated. So the mean value is still one of the most useful single numbers that you can find about a data set or a data stream. And the variance is just the close second. Sometimes the variance is even more important. I mean, actually, in most cases, the variance is even more important, but it doesn't give you all that much without the mean. It just looks at how far is it spread. So you have the mean for any point, and the variance is just some sort of interval around that. This will be very useful in later stages. We will see this in the second course again, and in the third course for the machine learning part. And the standard deviation is, it basically, I mean, it's just the square root of the variance. So it doesn't look all that interesting. It's typically used to conserve the unit, because so if you have a measurement that is in volts and then you do a variance of it, the variance of is in squared volts, that's kind of weird. So physicists often use the standard deviation. So after all the theory, I think it's time for an example that has some colors on it. So we're looking at various curves here, and actually 4 of them. And let me draw your attention to the red one in the middle. This is the so-called standard Gaussian or standard normal distribution. It is centered at 0, so the mean of the curve or of the data that is under the curve is the mean is 0. And it also has a standard variance, the variance of 1.0. You see this in the legend that the sigma squared equals 1.0. And what's happened here is that this is the unit Gaussian, the area under the curve, which is actually not possible to find in closed form, but the area under this curve is 1. It's exactly 1. And so what's happening is if we vary these 2 parameters, the mean and the variance, then we get different curves, of course. But they all hold that if you integrate all of them, then the area under them is 1.0. I mean, it's exactly 1. Which is to say If you make the variance smaller, like in the blue curve, the variance is smaller than in the red curve, so it's less far spread around the zero. I told you that the variance is a measure of how far the data is spread around the mean. And in this case, they share the same mean. Both the means are zero. But in the blue case, it's much narrower. So this can be looked at as some sort of measure of uncertainty. So we know that we're centered around zero, but now the question is how far? And we see that the blue curve is the most focused, let's say, of the distributions that we're looking at here. If we go in the other direction, we end up at this yellow, ochre, I don't know, the third curve, which has a sigma squared of 5.0. And this is much wider. And it's still centered around zero, so the mean is still zero, but it's much wider. Now, another thing we can change is, of course, the mean itself, which is this mu here. And this mu here has been shifted to -2, so it's centered around -2. And also the variance is slightly smaller than the standard unit Gaussian, which means that it's higher and narrower. Okay, beautiful. From this, we can look at actually something else. Turns out that many of these parameters are single values that we talked about are just special cases of the raw, central, and standardized moments. And the raw moments are, simply speaking, taking the kth power of each data sample, sum this up, and then divide by the number of samples that are in there. Maybe it's a little bit unintuitive why you would need this, but bear with me. The central moment, the kth central moment, is very similar, but it's centered in the sense that you subtract the mean first. So you look at some mean centered, so it's centered around the mean power of the data, and then you sum that up and divide by the number. There's one more thing, that this is a standardized moment. It's very similar to the central moment, except that you also divide by the kth power of the standard deviation. There are some very, very notable moments. The first raw moment, for example, is the mean. It's just the mean. Whereas the second central moment is the variance, and the third standardized moment is the skewness, and the fourth standardized moment is the kurtosis, which they measure certain things. For example, the skewness measures how much the distribution is tilted to the left and or the right, whereas the kurtosis measures the tail, so how far spreads the distribution of data. Typically, what you see when you arrive at the second moment, you always go for the centralized moment, because you're trying to figure out how does the data look like, and you're typically interested in how the data center behaves around the center. So this is kind of, it's comparable to a rotation. So you're shifting first to the center around that rotation, and then you realize at which angle you look at. Okay, from this we should move forward to something else. We're looking at probability mass functions now. So what we're trying here is we have some random variable, and we're also getting samplings from this random variable. So we don't really know the variable itself. Typically we cannot know the variable because they are unmodeled or impossible to model. But what we get instead is we get samples of it. So we're having n realizations of that random variable, and we're trying to figure out, okay, what should the next realization of that random variable be like? For this, we kind of model the random variable implicitly. So we're trying to estimate the true probability distribution of that random variable xj. So I want you to understand or to think about why this intuitive approach of doing something like the averaging before, or like the mean, So just counting the occurrences of some x, some realization, and then dividing by the number this occurrence happens. Why does this not work? So the answer to this is often cases we have x's or random variables whose domain is the real numbers. And the real numbers are uncountable. So the probability of the random variable being exactly some value that we predefine is zero. It's exactly zero. This is something with accountability. There's an argument for this. You can look up the proof if you're interested, but this would go too far here. But this doesn't work. So in this discrete domain, so to speak, what we're introducing is bins, and this is like a bucket, so to speak. So you're defining a certain area in which the random variable's realization should fall. And then you can define this probability measure here, which is just you integrate over the bucket, this specific bucket from going from A to B here. And if you're interested in finding, okay, is a realization within A and B, then we can just integrate over the realizations of that random variable. This can be approximated by using the indicator function and then just counting. This is exactly the approximation of what we're doing in the top, but we're using now specific buckets instead of a single number for realization. We can bring them arbitrarily close to one another, so we can make A and B be very, very close together, but you cannot make the distance between those two numbers zero, because if we make it zero, then we return to a point, and points are, you can have uncountable many points in the real number, in any slice of real numbers. So again, this collapses down to zero. Nice. So what we've done up until now is we looked at single features, single columns, if you will, in your database, and looked at how do they behave? What's the mean value? How does it behave? How does it change over time? What are some statistical quantities derivable from this single feature? But what you're often actually interested in is how do features interact? So how do single columns interact with other single columns? For example, how does the voltage change with the required power? Or does it change with the required power? Does it lag behind? Maybe things like this are typical use cases for a correlation. And this correlation basically measures the strength of the interaction between two random variables. So here we have two variables, x and xj and xk, and we're trying to figure out how closely do they resemble one another. So if one changes, does the other change as well? And this correlation rho here is just a tool to use. So it goes even further. So I should maybe point out that a high correlation means that the two values change in the same way. The two random variables realizations change in the same way. And a low correlation or even a negative one would imply that they change exactly vice versa. So if the one grows, the other falls. But there are two important points here that need to be understood. The first being that this captures only linear relationships. So if the correlation between two features were to be zero, you cannot be certain that they don't depend on one another somehow. You can only be certain that they don't depend on each other, or they don't vary with one another linearly, so in a linear way. There may still be some nonlinear interaction between the features. Maybe something that, or something that is time lagged or something like that. The second part, and this is very, very crucial, you as with a scientific background, you probably know this to be true, but correlation does not mean or imply causation. So even if two features vary basically the same way, you cannot say that this is because they are intrinsically linked. And this is something needed to understand. I mean, this is an indication, but it's by no way a proof. Okay, enough with the science or the science theory. Let's look at statistics again. So if you have access to the probability mass function, and this is something, okay, along the lines of what we've done in the last slide, if you have this mass function somehow, and not just samples for estimation, you can even go further and define the covariance. And the covariance is, there is a very nice analytical way of putting it here with the expected values E. This expectation is, as you remember, it's linear. The expectation is just an integral, and integrals are linear. And also the expectation of the expectation is, of course, the expectation itself, because the expectation of a single value is just a single value, and the expectation is a single value. Then the covariance of x and y can be put up like this. So it's the expected value of x centered around the x, its mean, and y as a times y centered around its mean. And then this distributes very nicely into this the second part. So you get the expectation of the x times y, and you subtract the means of the two multiplied together. You should go ahead and derive this yourself. This is, on the one hand, it's a nice exercise. On the other, it really prepares you well for the exam. But in any way, I mean, this is very simple. You should need less than 2 minutes. You can just remember these two parts here and then just do it yourself. I'm not waiting for you though. I mean, you should pause the video for this. So let's just go on for the correlation, which is just a normalized covariance, right? So the higher part, I mean, this is, if you have the samples, then you can also, so if you can sample from the covariance, the two random variables that make up the covariance, then you can also do the exact same thing as above. So you just take the samples, sum over them, and then divide by the standard deviations. And of course, I mean, it's a standard deviation for the first variable and the standard deviation for the second variable. This is crucial to understand here. There's actually a small typo in the slides. I will correct this. There's a sigma j, sigma y in the denominator. This should not be sigma y. It should be sigma x too, because we don't. Yeah, okay, you see it probably yourself. This correlation measures, as I said, the relationship, and especially the linearity of the relationship. Okay, so this was enough with the theory. What we're doing now is we're going to have a hands-on with Jupyter. This should work, but I really strongly encourage you to download Jupyter yourself. It's Python based, what we're doing, because Python is a beautiful language for some parts of the world. And it's very widespread and easy to use, easy to read. So if you don't know it yet, don't be afraid. You can read it like a book, basically. Things that you will need in the course, in the next sessions of this course and this course, because we're going to have hands-on in every session, are just the Jupyter Notebook, NumPy, SciPy, and Pandas, plus the plotting library Matplotlib. And this is something that can be installed on a Linux machine in less than 5 minutes. I have no clue about how this works on Windows. There should be some distribution that works, but I don't know. I've stopped using Windows 12 years ago, except in virtual machines, and those I don't use for any sort of development. So this is up to you, but you will figure this out. And if you can't, drop me an email. There may be solutions we can find. So go ahead and play with that. We will also supply the data, of course.